In this video, we'll talk about the fundamental theorem of calculus, which is one of the most important mathematical discoveries in history. It states that if f is continuous on the closed interval from a to b, then the function f of x, which is the antiderivative of x, is equal to the integral from a to x of f of t dt, has a derivative at every point x in the closed interval a to b, and if we take the derivative of each side, so the derivative of d dx of the integral from a to x, f of x dt, that'll equal f of x. That'll equal the function evaluated at the upper bound. So here's an example. Using the second part of this equation, if we want to find the derivative of the integral from negative pi to x of cosine of t dt, all we have to do is substitute the upper bound in for the variable that we're integrating in terms of. We're integrating in terms of t, so we substitute that variable in for t. So this is simply equal to cosine of x. Another example, we're going from 0 to x, and we want to find the derivative of this integral. We're integrating in terms of t, so I'm going to substitute the upper bound in place of t. So this is simply equal to 1 over 1 plus x squared. These two examples will help you with problems 1 through 8 on the problem set. Sometimes we'll need to apply the chain rule within the fundamental theorem of calculus. So in this example, our upper bound is x squared, not x. So we are going to change the upper bound to be u. So we're going to substitute x squared, or substitute u in for x squared. So we're going to say that y is equal to the integral from 1 to u of cosine of t dt, and we're going to state that u is equal to x squared. So we just did simple substitution, so that way we can use the rule that we used in these two examples. So we're going to have y is equal to, let's see, I'm going to take the derivative of this side, so I'm going to do dy dx, derivative is equal to d du, because I'm taking the derivative in terms of u from 1 to u of cosine of t dt times du dx. So if you remember from when we were doing differentiation, the chain rule said you have to do the derivative of the outer function times the derivative of the inner function. So this piece here is the derivative of our outer function, the outer function being the cosine t. This is the derivative of our inner function. Our inner function is x squared. So the derivative of this piece, just as we did in these two examples, we're going to plug the upper bound in for t. So this becomes cosine of u times the derivative of our inner function, the inner function being x squared. The derivative of x squared is 2x. So now to finish it up, I'm just going to put the 2x in front, but instead of cosine u, I'm going to substitute back in. Instead of u, I'm going to put x squared, so I'm plugging that back in. So just like we did with our derivatives, we're doing the derivative of the outer function times the derivative of the inner function. Here's another example like that. So we have this function here, but our upper bound isn't just a single variable. So I'm going to change this to be y is equal to 0 to u. So I'm replacing the x squared with u of e to the t squared dt, and I'm going to state that u is equal to x squared. So they can see where that substitution came from. Now I want to do the derivative of the outer function. So d du of our integral 0 to u of e to the t squared dt, that's the derivative of the outer function, times the derivative of the inner function, du dx. Using the fundamental theorem of calculus, I can substitute u in for t to evaluate this derivative. So this becomes e to the u squared times the derivative of the inner function. The derivative of x squared is 2x. So now putting it all together, I'm just going to move the 2x out front times e. Instead of u, I'm going to replace that back with x squared. And I also have this squared here. Parentheses should be there. So this becomes 2x times e to the x to the 4th power. These two examples will help you with problems 10 through 12. So if you want to pause the video and do those two examples help you with that. Now in some instances, the lower bound will be a variable, so we have to deal with that. If the upper bound is a constant and the lower bound is a variable, we can use one of our integral rules from the previous section. So our first integral rule said if we change the order of the bounds, all we have to do is negate it. So that's what we're going to do here. We're going to find the derivative, so dx of x to the x from x to 5, 3t sine t dt is the same as the derivative of the negative integral from 5 to x. So all I did is switch the order of the bounds and negate it. That's our first integral rule. I keep the function the same. And now I'm able to apply the first fundamental theorem of calculus, where I just substitute this upper bound in for t. So this becomes negative, there's our negative, 3x, because x went in for t, of sine x, the x went in for t there again. This will help you with problems 13 through 18, if you want to try those. And some of them, some of the later problems here, you'll have to switch the bounds and then apply the chain rule like you saw in the previous example. So now our last one, we have variables on the upper and lower bounds. So to evaluate this, we're going to break this apart into two pieces. So we're going to find the derivative of the integral from 0 to x squared. So I'm using the upper bound here. The function will be the same, 2 plus e to the t dt, minus integral from 0 to 2x. So now I'm using the lower bound. The function is the same. So I'm going to need to apply the chain rule as well as the fundamental theorem of calculus. So I'm going to take this piece and substitute it in for e. So this becomes 1 over 2 plus e to the x squared. So the x squared went in place of t, times the derivative of the inner function being x squared, so that would be 2x. So this whole thing went down to this. The derivative of the outer function using the first fundamental theorem of calculus times the derivative of the inner function. So I apply the chain rule there, minus. Now I need to do all of this. I can substitute 2x in place of t. So I get 1 over 2 plus e to the 2x times the derivative of our inner function, which is this. So that just becomes 2. Now just to make it look a little bit neater, I'm just going to put these constants up into the numerator. So I get 2x over 2 plus e to the x squared minus 2 over 2 plus e to the 2x. So that put together the chain rule and the first derivative rule. This will help you with problems 19 through 20.